Today we are looking at constraint optimization with bordered Hessian methods. Our learning objectives are to construct and compute Lagrangians, compute gradients including derivatives with respect to lambda, solve constraint optimization problems, I should probably say, calculate bordered Hessians, calculate the projected bordered Hessian, use them to classify constraint optima, and then finally looking at the bordered principal minors method in order to classify the optima of a constraint optimization problem. If we just look at what constraint optimization is, from last lesson, from last time, we saw that agents want to maximize so many different things: their opinions, returns from investments, utility gain from consumption, and that's just to name a few. But sometimes the agents are constrained on the available choices that they have due to other factors, such as income. So, for example, their utility gauge from consuming two or more goods is constrained by their income or budget. So constraint optimization allows us to find the optimum values of an agent subject to their constraints. We do this by using the Lagrangian. So this is the Lagrangian. You can have lambda at the start or at the end. I'll just put it at the start because we don't really know how many variables there are, because this is just the general form. So the Lagrangian is a function with variables lambda, x1, x2, all the way up to xn, and it is equal to the function f, which is a function of x1, x2, all the way up to xn, and this is the function that we want to maximize, plus lambda g of x1, x2, all the way up to xn, and this is our constraint. So it's always the function we want to maximize plus lambda, the constraint. So just regurgitating what I said, this is the equation for the Lagrangian, where we have the function f of x1, x2, all the way up to xn, when we want to maximize subject to the constraint g of x1, x2, all the way up to xn, which is equal to 0. And lambda is known as the Lagrange multiplier. The process for finding constraint optima using the Lagrangian is step number 1, define the Lagrangian in terms of the function you want to maximize and the constraint under which you optimize it. Second step would to calculate the first order conditions of the Lagrangian. Step number 3 is to solve said first order conditions for the local constraint optima. Step number 4 is to calculate the Hessian, and then step number 5 is to classify the type of constraint optima. And this is where the projected bordered Hessian comes in and the bordered principal minors method. But before we get onto that, just looking at the first order conditions of the Lagrangian, this would be a very sophisticated way of expressing the first order conditions. We take the Lagrangian, differentiate it with respect to lambda, with respect to x1, all the way up to the last variable, which is in this case xn, and we equate it to 0. So all of these will be equal to 0. And when we work out the first order conditions, we are just working out the gradient. So find the gradient of the Lagrangian with respect to each of the variables, lambda, x1, x2, x3, all the way up to xn, and set it to 0. And the partial derivative with respect to lambda considers the constraint. Or we can just say it is the constraint, because when we differentiate with respect to lambda, we just get the constraint. Cool. Looking at the bordered Hessian, for a function which has two variables x and y, subject to the function that is a constraint, which is going to be g, which is a function of x and y, which is equal to c. The bordered Hessian is 0, partial derivative of the constraint with respect to x and y over here. That's the same over here. And then this internal matrix is just the Hessian, hence why it's called a bordered Hessian. So for a constraint optimization problem of functions of two variables, and where there is one constraint, the Hessian is a 3x3 matrix. That's what's happening here. We've got two variables x and y and just one constraint. So we've got 3x3 matrix. And what we should be able to see is that the first row and the first column is just the gradient of the constraint with respect to lambda, x and y, and then the rest is just an ordinary Hessian. Cool. Again, this is just the general Lagrangian, and if we write the general bordered Hessian, it would look like this. So we've got the gradient over here and over here, and then over here we've just got the Hessian. So we've got the second order partial derivatives with respect to x1, x2, all the way up to xn, and then we've got the mixed partials over here. Cool. Moving on to ways to classify the nature of the optima. One way is to use the projected bordered Hessian. Step number one is to find the projected matrix, which hopefully you watched a video where we covered that. And this is where we do P is equal to I minus U ut over utu, or we could just do P is equal to I minus normalized vector u tensor with itself, where u is the gradient of the constraint. So on the projected matrix, you would find the gradient of the constraint with respect to lambda x and y. You would then normalize the gradient vector, then work out the projected matrix by doing the identity matrix minus the tensor product between the normalized gradient vectors. So over here, I'm basically explaining this method, but this is also valid. Step number two is to then sandwich the bordered Hessian between the two projected matrices. So we'd have the projected matrix, which I'll call P, the bordered Hessian, which I'll call H subscript B, and then another projected matrix. And then finally, you would find the eigenvalues of the projected bordered Hessian to determine the nature of the local optima. Instead of projecting the bordered Hessian, what we can do is also project just the Hessian. So this is the exact same approach. We find the gradient of the constraint with respect to variables in the constraint. So all I mean by that is just we work out the partial derivatives of the constraint, but we exclude lambda. Using this, we find the projected matrix and sandwich this in between our usual Hessian and find the eigenvalues. So the difference with these methods is when we just project the Hessian, it gives us one zero eigenvalue and another non-zero eigenvalue, and this non-zero eigenvalue will tell us whether it's a maximum or minimum. With the projected bordered Hessian, it gives us two eigenvalues, which are 0, and then another non-zero eigenvalue, and this non-zero eigenvalue will tell us if it's a maximum or a minimum. So looking at those eigenvalues, if the eigenvalue is positive, it means that we have a local minimum. If it is negative, it means that we have a local maximum. And if it is mixed signs, then we have some sort of saddle point. Now, looking at the bordered principal minus method, which I think it's a bit easier and a bit quicker than projecting the bordered Hessian. The principal minors are the determinants of the square submatrices formed within the bordered Hessian matrix. So, say I had this Hessian over here. A submatrix, a square submatrix of this Hessian would be this matrix, which will be 0, 1, 3, 4. And then another one would be just the whole matrix. So that's what we mean by submatrix. Moving on. So for the case of n choice variables, so some number of variables and m is equal to 1, where m represents the number of constraints, the bordered Hessian is an m plus 1 times m plus 1 matrix. With m is equal to 1, one constraint and two choice variables, the bordered Hessian is a 3 by 3 matrix, which is what we saw before. In calculating n minus m, so the number of variables minus the number of constraints, which in this case is 2 minus 1, which equals 1, tells us that there will only be one relevant minor, which in this case is the determinant of the entire 3 by 3 matrix. So if this was our bordered Hessian, then the only relevant matrix of minor would just be the determinant of the whole matrix. If we now had 3 variables and still just one constraint, the bordered Hessian is a 4 by 4 matrix, and there are now 2 minors, which we calculated by doing n, which is 3 minus m, which is 1, so 3 minus 1 is 2, so there's now 2 minors, and the determinant of the upper level 3 by 3 matrix, and the determinant of the 4 by 4 matrix. That sentence doesn't quite make sense, but what I'm trying to say is we now have to consider a 3 by 3 matrix, and we have to consider the matrix of the whole bordered Hessian. So again, if I now draw a 4 by 4 bordered Hessian, we will work out the determinant of this 3 by 3 matrix, and we will also be working out the determinant of the whole matrix. Now, using these determinants, we can tell if our optima is a minimum or a maximum. So for a local maximum, when there is one constraint, the smallest minor must have sign -1 to the power of m plus 1. For us, m is always 1, so we do -1 squared, and -1 squared is, of course, 1, which is positive. So our smallest minor should be positive. So with two variables and one constraint, there's just one minor to check, because over here we just had one minor, which happened to be the determinant of the whole matrix, and that one minor must be positive. If we had three variables now, we would have the 3 by 3 matrix, and then we would also have the 4 by 4 matrix. So the first minor, which is the 3 by 3 matrix, would have to be positive, and then the second minor, which is the determinant of the whole bordered Hessian, would have to be negative. And the sort of general rule is for a maximum is that the signs alternate starting from positive. So it'd be positive to negative, back to positive, and negative, going back and forth like that. If we now had a local minimum, again, for just one constraint, all the relevant minors must have the sign -1 to the power of m, where m is the number of constraints. For us, m is always 1, so we do -1 to the power of 1, which of course is -1, which is negative. So they must all be negative. So with two variables, there's just one minor to check, and it must be negative. With three variables, both minors need to be negative. So for a local minimum, we use this rule, and it turns out to be negative, and we want all the minors to be negative. So if it happens to be that all the minors are negative, it means that we have a local minimum. Cool. That was a lot of theory, so we'll do some questions and hopefully we can see all that theory in action. Question 1. A consumer maximizes utility, which is a function of x and y, is equal to x to the power of 0.5, y to the power of 0.5, subject to the budget constraint 2x plus 4y is equal to 100. Write down the Lagrangian, compute all three conditions, solve for the optimal, calculate the Hessian and bordered Hessian, use the projector method to classify the nature of the optima. Cool. If we write down the Lagrangian, we get x to the power of 0.5, y to the power of 0.5 plus lambda 2x plus 4y minus 100. We always want to make the constraint equal to 0. If we now compute all the first order conditions, we partially differentiate the Lagrangian with respect to x, which gives us 0.5x to the power of minus 0.5 multiplied by y to the power of 0.5 plus 2 lambda. Partially differentiating with respect to y gives us 0.5x to the power of 0.5 multiplied by y to the power of negative 0.5 plus 4 lambda. And partially differentiating with respect to lambda just gives us the constraint, which is 2x plus 4y minus 100. Like we mentioned before, first order conditions are always equal to 0, so we can equate all of these to 0. What I will now do is times this equation by 2, so that we get x to the power of negative 0.5 multiplied by y to the power of 0.5 plus 4 lambda is equal to 0. And rewriting this equation, we get this. So now what we can do, because they're both 4 lambda, we can equate these two together. Essentially what I'm doing is moving these two to the other side, so we have minus 4 lambda is equal to this, and then minus 4 lambda is equal to this, and then equating the two minus 4 lambdas, so that we get x to the power of 0.5, y to the power of 0.5 is equal to 0.5, x to the power of 0.5, y to the power of minus 0.5. This should be plus. Cool. If we now collect like terms, we get y is equal to 0.5x. That is just me moving this y to the other side. So we do y to the power of 0.5 divided by y to the power of minus 0.5, which is y. And then moving x to this side, we do x to the power of 0.5 divided by x to the power of minus 0.5, which is x. So we get this. If I now substitute this equation, which I'll call equation 3, into this equation, which I'll call equation 4, we get 2x plus 4 brackets 0.5x minus 100 is equal to 0. This we can rearrange so that we get 2x plus 2x is equal to 100. So 4x is equal to 100. So x is equal to 25. Using this, we know that y must be equal to 25 over 2 then. And now if we substitute this into, let's say, our second equation, we get 0.5 brackets 25 to the power of 0.5 is just 5. And then 25 over 2 to the power of negative 0.5 is just root 2 over 5. And then plus 4 lambda is equal to 0. So now we get 4 lambda is equal to minus root 2 over 2. Because those and those cancel, and then 0.5 is just a half. And then dividing by the 4, we get minus root 2 over 8. So lambda is equal to minus root 2 over 8. So this is our optima. If we now calculate the Hessian and the bordered Hessian, we'll begin by calculating the Hessian, which is just finding the second order partial derivatives. So differentiating this with respect to x again, we get, calculating the mixed partials, we get, and then calculating, and then differentiating this partially with respect to y again, we get minus 1 over 4, x to the power of 0.5, y to the power of minus 1.5. If we now substitute in our optima, we get minus 1 over 4 multiplied by 1 over 125. That is because 25 to the power of 1.5 is just 25 times 5, which is 125. But this is negative, so we write that as 1 over 125. And then y to the power of 0.5 would be 5 root 2. Doing the same over here, we get 1 over 4 multiplied by 1 over 5 multiplied by root 2 over 5. And substituting in here, we get minus 1 over 4 multiplied by 5 multiplied by 2 root 2 over 125. If we simplify this a bit more, we get minus 1 over 4 brackets 1 over 25 root 2, 1 over 4 root 2 over 25, 1 over 4 root 2 over 25, and then minus 1 over 4 2 root 2 over 25. If I now work out the bordered Hessian, we get 0, 2, 4. That is because our constraint was 2x plus 4y is equal to 100. So differentiating this with respect to x partially is just 2. Differentiating with respect to y partially is just 4. And that is the same over here. And then we can just rewrite our Hessian. And we can also simplify it a bit further. So we get minus 1 over 100 root 2 over 100. And then minus 2 root 2 over 100. Cool. If we now use the projector method to classify the nature of the optima, then if we use the formula P is equal to the identity matrix minus U multiplied by u transposed, and then u transposed multiplied by u, where our vector u is going to be 0, 2, 4. We get p is equal to I minus, if we look at the bottom first, u transposed multiplied by u is 0, 2, 4 multiplied by 0, 2, 4, like this. So we do row times the column, which is just 0 times 0, 2 times 2, which is 4, 4 times 4, which is 16, 16 plus 4 is 20. So we get 1 over 20, and then doing 0 to 4 multiplied by 0 to 4, we get 0, 0, 0, 0, 4, 8, and then 0, 8, 16. So 0 times each of these, and then 2 times each of these, hence why 0, 4, 8, and then 4 times each of these. Cool. If we now do the identity matrix minus 1 over 20, this new matrix, we get 1, 0, 0, and the zeros over here stay the same. And then we do 1 minus 4 over 20 for this middle term, which is 4 over 5. Then we do 0 minus 8 over 20, which is minus 8 over 20, which we can simplify to minus 2 over 5. That's the same over here. And then we get 1 minus 16 over 20, which is 1 over 5. So this is our projector matrix. Now, if we sandwich this matrix between the Hessian, we get this. If we now multiply these two matrices together, we get 0, 0, 0, and then 2 when we do that, and then 4 over here when we do that. Then we should do this row multiplied by this column, and we get minus 0.0113. I'd recommend doing as many decimal points as possible. So in this case, I'm going to do 5 decimal places. Over here we get 0.00566, and that's been rounded. Over here we get 0.02263, which again has been rounded. And over here we get minus 0.01131. Now, if we multiply these two matrices together, we get 0, 0, 0. This times this column gives us 8 over 5 minus 8 over 5, which is 0. This times this gives us minus 4 over 5 plus 4 over 5, which is, again, just 0. So now if we do this row times this column, we get minus 0.099532. If we work out this entry, we get 0.00905, which is the same over here, which is a good sign. And over here we get minus 0.004526. Cool, so this is our projected bordered Hessian. What we now need to do is find the eigenvalues. So we have that of this Hessian, which I'll just call PBH minus lambda I, and equate that to 0, and that's going to give us our characteristic equation. So we get minus lambda 0, 0, 0, 0, minus 0.099532 minus lambda 0, 0, 0, 9052, 0, 0, 0, 9052, and then minus 0.004526 minus lambda. Equate that to 0. If we work out the determinant now, luckily this is really easy because these two are 0, so we just get minus lambda minus 0.099532 minus lambda 0.009052, 0.009052 minus 0.004526 minus lambda. Equate that to 0, so we get minus lambda brackets these two multiplied together, and then these two multiplied together. So we get this. So we already know that one solution or one answer is going to be that lambda is equal to 0. And then if we expand all of this, we would get the other eigenvalues. What we can also do is just look at this matrix. If we just look at this matrix, then we can use the rule to go straight to the characteristic equation, which is lambda squared minus the trace of this matrix, lambda plus the determinant of this matrix is equal to 0. So we get lambda squared minus the trace, which is both of these added together, which is negative 0.104058. So that becomes positive now. And the determinant is 0.00368543 is equal to 0. So this gives us minus 3.671238081 times 10 to the negative 3, and also gives us minus 0.10038867. Okay, it does seem that I've lost the ability to use a calculator, and this value should have actually been 0.0181. So this over here does change, so does this, and so does this, and so does these two values. Should get 0.022626, and then as the determinant, you will get a very tiny number of minus 1.8104 times 10 to the minus 8. And so you get your eigenvalues as 8 times, or 8.001131 times 10 to the minus 7, and then minus 0.0226. So as I mentioned before, when you have the projected boarded Hessian, it gives you two 0 eigenvalues and another non-zero eigenvalue. So in our example over here, we have this 0 eigenvalue. This is practically 0 because you're doing 0.000008001113. So this is practically 0, and then we get this non-zero eigenvalue. As we can see, this non-zero eigenvalue is negative. So if we go back to our table, a negative eigenvalue means it is a local maximum. So classify the nature of the optima, it is a maximum. So just to check this, what we can do is work out the determinant of the boarded Hessian, because that is what the principal minus method says to do. When we have two variables and one constraint, all we need to do is just work out the determinant of the boarded minus method, of the boarded Hessian, and see whether it's positive. If it is positive, then we have a maximum. So if we use the diagonal way, this is 0, this gives us a root 2 over 100, this gives us another 8 root 2 over 100, and minus this, which is minus 8 over 100 root 2, this which is 0, and then this which is minus 8 root 2 over 100. So as you can see, this is definitely going to be positive and hence greater than 0, so we have a maximum. That's because positive plus positive is obviously a positive number. Then these two subtracted will give us a negative number, but then we're subtracting from that negative number, or subtracting that negative number, which means that we are actually adding. So this should be a positive number, so we have a maximum. Moving on to question 2. Maximize f, which is a function of x, y, and z, which is equal to x plus 2y plus 3z, subject to the constraint, which is a quadratic constraint. X squared plus y squared plus z squared is equal to 14. Write down the Lagrangian, derive and solve the first order conditions, construct the boarded Hessian, use the boarded principal minus method to classify the nature of the optima. So the Lagrangian is going to be x plus 2y plus 3z plus lambda x squared plus y squared plus z squared minus 14. Our first order conditions are going to be 1 plus 2x lambda, 2 plus 2y lambda, 3 plus 2z lambda, and then x squared plus y squared plus z squared minus 14. If we make lambda the subject for each of these, we get lambda is equal to 1 over 2x. Over here we get lambda is equal to minus 1 over y, and over here we get lambda is equal to minus 3 over 2z. If we equate this equation, which we'll call number 1, with this equation, which we'll call number 2, we get 1 over 2x is equal to 1 over y. They were negative, but we just times by negative, so they both become positive. And so we get y is equal to 2x over here. Equating equation 1 with this equation, which we'll call equation 3, we get 1 over 2x is equal to 3 over 2z. So 2z is equal to 6x, and so z is equal to 3x. So we get a general solution of x, 2x, and then 3x, because y is the same as 2x and then z is the same as 3x. Substituting in this general solution into our constraint will get us the particular solution. So if we do that, we get x squared plus 4x squared plus 9x squared is equal to 14. So 14x squared is equal to 14. So x squared is equal to 1. So we get x is equal to 1 or x is equal to minus 1. So if we now use that to work out y, z, and lambda, so x is equal to y, x is equal to 1, y is equal to 2, and then z is equal to 3. So that's just me substituting in 1 into here. If x is equal to minus 1, y is equal to minus 2, z is equal to minus 3. And if we work out what lambda is, using this equation, we know that lambda is equal to minus 1 over 2x. So over here it's just going to be minus a half, and over here it will just be positive a half. Cool. If we now work out the bordered Hessian, this will be 0, differentiating the constraint partially with respect to x, y, and z gives us 2x, 2y, 2z respectively, and that carries on over here. If we now differentiate this again with respect to x partially, we just get 2 lambda, and because it has no other variables, differentiating it with respect to y and z just gives us 0. That's the same over here. Differentiating this with respect to y just gives us 2 lambda, and then differentiating this with respect to z just gives us 2 lambda again. So if I substitute in 1, 2, 3, and then minus a half into here, we get 0, 2, 4, 6, and then 2 minus 1, 0, 0, 4, 0, minus 1, 0, 6, 0, 0, minus 1. If we use the bordered principal minus method, we will have to work out the determinant of the 3x3 submatrix, which, if we use the diagonal method, gives us 0 plus 0 plus 0 minus, this is minus 16, 0, and then this gives us minus 4. So the determinant is 20. If we now work out the determinant of the whole 4x4 matrix, we can just ignore this because it's just 0, and so keeping in mind that those are our cofactors, we get minus 2, and our matrix of minor, when we ignore that row and column, is 2, 0, 0, 4, minus 1, 0,
6, 0, minus 1. Then we get plus 4, 2, minus 1, 0, 4, 0, 0, 6, 0, minus 1, and then plus 6, 2, minus 1, 0, 4, 0, minus 1, 6, 0, 0. Cool. If we work out the determinants now, this is 2, this gives us 0, this gives us 0, this gives us 0, this gives us 0, and then this gives us 0. So the determinant of this matrix is just 2. Now working out the determinant of this gives us 0, these multiplied together give us 0, this multiplied together gives us 0, this multiplied gives us 0, this multiplied gives us 0, and then minus 1 times 4 times minus 1 is 4, but we need to minus that 4 from the rest, so we get minus 4. If that didn't make sense, that's because we are basically doing 0 plus 0 plus 0 minus 0 plus 0 and then plus 4, so it ends up that is minus 4 as the determinant. And lastly, this is 0 minus 1 times 6 is 6, 0 times that is just 0, these 3 times together is 0, these 3 times together is 0, and these 3 times together is 0. So the determinant of this is just 6, so we get minus 4 minus 16 minus 36, which is minus 56. So we can see that D3 is positive, and then D4 is negative. We've got our alternating pattern with the first one being positive, so we know that this is a maximum. Cool. And I will let you do this one in your own time. Moving on to question 3 now, which is quite a large question, something that we might actually see in the exam. Consider the function f, which is a function of x, y, and z, which is equal to x to the power of alpha, y to the power of beta, and z to the power of gamma, where alpha, beta, and gamma are both greater than 0, and alpha plus beta plus gamma is equal to 1, subject to the constraint g of x, y, and z, which is equal to b minus p x of x minus py y minus pzz for sum b, which is greater than 0, and for prices px, py, pz greater than 0. Write down the Lagrangian for the optimization problem, compute the gradient of the Lagrangian, and derive the first order conditions and solve them. Compute the bounded Hessian using the bounded principal minus method to classify the optima. If we write down the Lagrangian, we get x to the power of alpha, y to the power of beta, z to the power of gamma, plus lambda b minus px, x minus py minus pzz. Partially differentiating this with respect to x, we get alpha x, alpha minus 1, y to the power of beta, z to the power of gamma minus px lambda. So we get this. If we now equate equation 1 and equation 2 with each other, if we make lambda the subject for equation number 1, we get alpha x to the power of alpha minus 1, y to the power of beta, z to the power of gamma, all over px is equal to beta x alpha y beta minus 1 z gamma all over py. If we now cross multiply and divide by z to the power of gamma, we get py multiplied by alpha multiplied by 1 over x. That is me just doing x to the power of alpha minus 1 divided by this, which just gives me x to the power of minus 1. And that is equal to px multiplied by beta multiplied by 1 over y. So again, doing this divided by this. And we can cross multiply and get alpha py multiplied by y is equal to beta pxx. And this can be written as y is equal to beta pxx all over alpha py. Cool. If we now equate equation 1 with equation 3, we get gamma x to the power of alpha, y to the power of beta, z to the power of gamma minus 1 all over pz is equal to alpha x to the power of alpha minus 1, y to the power of beta, z to the power of gamma all over px. If we first divide by y to the power of beta and cross multiply, we get px multiplied by gamma multiplied by 1 over z is equal to pz multiplied by alpha multiplied by 1 over x. So again, this is me doing x to the power of alpha minus 1 divided by x to the power of alpha, and over here to get 1 over z, I did z to the power of gamma minus 1 divided by z to the power of gamma. Cross multiply, we get gamma px multiplied by x is equal to alpha pz multiplied by z, and this can be rewritten to make z the subject, and so we get z is equal to gamma px x over alpha pz. So now we have some sort of general solution because we have y in terms of x and we have z in terms of x. So if we rewrite our constraint, which was px x plus pyy plus pzz is equal to b. Substituting in our general solution, so of course x is the same, but now y can be expressed as beta pxx over alpha py, and then z can be expressed as gamma pxx alpha pz, and that's equal to b. What we can now do is get rid of the py and the pz over here, and so we're left behind with pxx plus beta pxx over alpha plus gamma pxx alpha is equal to beta. If I now make alpha a common denominator, we get alpha over here, so I had to times this by alpha, so we get alpha pxx plus beta pxx plus gamma pxx is equal to b. What I can now do is factorize out pxx, and I'm left behind with alpha plus beta plus gamma all over alpha is equal to b. And if we have a look back at the question, we know that alpha plus beta plus gamma is equal to 1. So we get pxx over alpha is equal to b, because all of this is just 1. If we make x the subject now, we get alpha multiplied by b all over px as our value for x. If we now rewrite y in terms of x, we had beta px divided by py multiplied by x, but we can replace that x with alpha beta px, this, so we can cancel out the px, also there should be an alpha here, and we can cancel out the alpha, so we get y is equal to beta multiplied by b, so those two things are different, divided by py. And then finally for z, we can do gamma px over alpha pz multiplied by x, which is alpha beta over px. So again, we can get rid of the px, get rid of the alphas, and so z is equal to gamma b over pz. Cool, so this is our optima. Now to find the nature of the optima, we are of course going to have to calculate the bordered Hessian. So we have 0, px, py, and then pz, and that follows over here. So if we now differentiate partially this with respect to x again, we get alpha brackets alpha minus 1, x to the power of alpha minus 2, y to the power of beta, z to the power of gamma. Differentiating with respect to y gives us alpha beta, x to the power of alpha minus 1, y to the power of beta minus 1, z to the power of gamma, and differentiating with respect to z gives us alpha gamma, x to the power of alpha minus 1, y to the power of beta, z to the power of gamma minus 1. Doing the second row now, we know that this is going to be the same because the bordered Hessian is symmetrical. So we can just copy this and just paste that over here. And we know that this is also pz, and that due to symmetry, we can paste this over here. Now, if we differentiate this with respect to y, we get beta, brackets beta minus 1, x to the power of alpha, y to the power of beta minus 2, and then z to the power of gamma. And differentiating with respect to z, we get beta, gamma, x to the power of alpha, y to the power of beta minus 1, and then z to the power of gamma minus 1. And again, by symmetry, this is going to be the same over here. And so all we have to do now is differentiate this with respect to z. And so we get gamma, gamma minus 1, x to the power of alpha, y to the power of beta, and then z to the power of gamma minus 2. So now, if we use the bordered principal minus method, we're going to have to work out the determinant of the 3×3 submatrix, and then we'll have to work out the determinant of the whole matrix. So all of this is our 3×3 matrix. If we do that first, this multiplies to get 0. These two, these three multiply to make some sort of positive number. We know that because the prices are of course positive, and this differential is alpha times beta. And we know that alpha and beta are both greater than 0, and so timesing them together will make a positive number. So positive. And we don't really care about the powers, because if we had 5 to the power of 0.5 minus 1, that's still a positive number. And we know that all of these are positive. Cool, so we had this, which is positive, and then if we do this, it's also going to be positive. So I will label that with a P for positive. Then we do minus these three multiplied together. This is going to be negative because py times py is positive, but then py times py times alpha, brackets alpha minus 1. Alpha is a positive number less than 1 but greater than 0. So that's going to be 0.3. We know it has to be less than 1 because alpha plus beta plus gamma is equal to 1. And then we also know that alpha, beta, gamma is greater than 0. So let's say it's 0.3. That means we do 0.3 times 0.3 minus 1. So 0.3 times minus 0.7, which is negative. So these three multiplied together is going to be negative. So I denote that with n. Then we get these three times together, which is just 0. And then we get these three times together, which again by the same logic as before is also negative. So then we get two positives, which make a positive, and then we are doing minus a negative. So when we minus a negative, it turns out it's positive, so we're doing a positive plus a positive, which means that this is positive, so d3 is greater than 0. If we now work out d4 using a very similar approach, what we first have to do is do minus px and then the submatrix, which I'll write as px, py, pz, and then alpha, beta, beta, beta minus 1, beta, gamma, and then alpha, gamma, beta, gamma, gamma, gamma minus 1, plus py, which will be px, py, pz, alpha, alpha minus 1, alpha, beta, alpha, gamma, alpha, gamma, beta, gamma, gamma, gamma minus 1, and then finally minus pz, and then px, py, pz, alpha, alpha minus 1, alpha, beta, alpha, gamma, alpha, beta, beta, beta minus 1, and then beta, gamma. Cool. If we start working out the determinants, we're just thinking about if the determinants are going to be positive or negative for these 3x3 matrices. Over here, we're going to get positive times a negative times a negative. So positive times negative is positive, plus these three times together is positive, and then these three times together is also positive. And we're going to minus this with these three times together, which is going to be a negative because this is positive, this is negative, and this is positive. So positive times positive is a negative. These three times together is a positive, and then these three times together is a negative. Then we get plus py. We do these three times together, which is a negative. Then we get these three times together, which is another negative. Then we get these three times together, which is a positive. Then we get these three times together, which is a positive. These three make a positive, and then these three also make a positive. And then minus pz. These three times make a positive. These three times together make a positive. These three times together make a positive as well. We are subtracting that from these three, which make a positive. These three make a negative, and then these three also make a negative. Cool. So now we got to think about these three are all positive. This is two negatives and then a positive. So we can assume that altogether this is likely to be positive when we compute it. This one, if we think about it altogether, we've got positive number and we're going to subtract that from this, which looks like a negative number. So this is most likely going to be a negative. Over here, we've got a positive number minus what looks like a negative number. So this is likely to be positive. And so we get minus times a positive, which gives us a minus or negative. Over here, we've got positive times a negative. So we've got another negative. And over here, we've got another negative. So we can say that d4 is going to be less than 0. So over here, we had greater than 0. Over here, we had less than 0. So we know that this is going to be a maximum. Cool. Moving on to question 4. Consider if minimizing cost, where the cost function is equal to x squared plus xy plus y squared, subject to the production constraint, which is a function of x and y, which is equal to x to the power of 0.5, y to the power of 0.5 minus q, which is equal to 0 for some for some target output Q, which is greater than 0. Write down the Lagrangian for the optimization problem. Compute the full gradient of the Lagrangian, solve the first order conditions to find the optima. Compute the Hessian of the Lagrangian and boarded Hessian. Use the boarded principal minus method to classify the optima. Okay, cool. If you write down the Lagrangian, we have x squared plus xy plus y squared plus lambda x to the power of 0.5, y to the power of 0.5 minus q. If we now work out the first order conditions, we get this, and this is with respect to lambda. If we now label this equation 1 and this equation 2 and make lambda the subject, we get 2x plus y divided by minus 0.5x to the power of minus 0.5 y to the power of 0.5 is equal to this rearranged to make lambda the subject, which gives us minus 2y plus x all over 0.5 x to the power of 0.5 y to the minus 0.5. We can make these both positive, and if we cross multiply, we get 2x plus y brackets x 0.5 y to the power of minus 0.5 is equal to 2y plus x brackets x to the minus 0.5 y to the power of 0.5. So I've also got rid of the 0.5s as well in one move. If we now move this x to this side and move this y to that side, over here we get x, because x to the power of 0.5 divided by x to the power of minus 0.5 is just x. And on this side, we get y, because y to the power of 0.5 divided by y to the power of minus 0.5 is y. So now we get 2x squared plus xy is equal to 2y squared plus xy. These two cancel out, so we get 2x squared is equal to 2y squared, which is just x squared is equal to y squared. This equation, if we substitute it into the constraint, so we get y squared to the power of 0.5, y to the power of 0.5 is equal to q. We get y multiplied by y to the power of 0.5 is equal to q. So y to the power of 3 over 2 is equal to q. Y is equal to q to the power of 2 over 3. And if we work out the value of x, we'd get, again, q to the power of 2 over 3. If we now work out the Hessian, we get 2 plus 0.25, should be 2 minus 0.25, x to the power of minus 1.5, y to the power of 0.5 lambda. Over here we get 1 plus 0.25 x to the power of 0.5 y to the power of minus 0.5 lambda. Over here we get 1 plus 0.25 x to the power of minus 0.5 y to the power of minus 0.5 lambda. And then over here we get 2 minus 0.25 x to the power of 0.5 y to the power of minus 1.5. If we now work out the boarded Hessian, we get 0, 0.5 x minus 1 minus 0.5 y 0.5. Over here we get 0.5 x 0.5 y minus 0.5. And that follows the same over here. And then we can just copy the Hessian. And so we get this. So because we have two choice variables and one constraint, we just need to work out the determinant of this whole matrix, and that will tell us the nature of the optimum if we use the principal minus method, boarded principal minus method. So these two times together gives us 0. These two times together will give us 0.25, and then x to the power of 0.5 times x to the power minus 0.5 is just 1, and then that's the same with these two times in together. So we just get 0.5 times 1 plus 0.25 x minus 0.5 y minus 0.5 lambda. And then over here, we get the exact same thing. So these two times together will just give us 0.25, and then this is the exact same as that. So there is 2 lots of these, and we're going to minus that with these times together, which is just 0.25 brackets 2 minus 0.25 x to the power of minus 1.5 y to the power of 0.5 lambda. These 3 times together is just 0, and then timesing these 2 together is a bit different because this time y is to the power of minus 1.5, so we have to do minus 0.25 brackets 2 minus 0.25 x to the power of 0.5 y to the power of minus 1.5 lambda. Cool. So when we do that, we get d3 is equal to 0.5 plus 0.125 x to the power of minus 0.5 y to the power of minus 0.5 lambda minus these 2. What I will do is substitute in this equation into here just to make life a bit easier. So x squared is equal to y squared. So we get d3 is equal to 0.25 brackets 1 plus 0.25 y to the power of 0.5 lambda minus 0.25 2 minus 0.25 y to the power of minus 2.5 lambda minus 0.25 2 minus 0.25 y to the power of 0.5 lambda minus 0.5. Cool, so this is what we get now when we expand everything out. If we go back here and work out the value of lambda, we have, subbing it into the first equation, 2x plus y is equal to, plus 0.5 x to the power of 0.5 minus y to the power of 0.5 lambda is equal to 0. We get 2q2 over 3 plus q2 over 3, which would just be 3q2 over 3 plus 0.5 1 over q 1/3 and 1 over q 1/3. Lambda is equal to 0. So this is 3q2 over 3 is equal to minus 1 over 2q2 over 3 lambda. So we get 6q4 over 3 is equal to minus lambda. So minus 6q4 over 3 is equal to lambda. Cool. So using that knowledge, we know that these do cancel out. This is going to be negative. This is going to be a negative, and this is going to be a negative, and this is already negative. We know that d3 is going to be some sort of negative number. Hence, this will be negative, and when this is negative, we have a local minimum. Cool. A very long session. Hopefully that was all useful and made sense to you, and you have a much better understanding and ability to solve constrained optimization problems. If you found this video helpful, please do subscribe and donate to my Buy Me a Coffee page. Thank you very much.